Thank you. So today I'm going to talk about the nanomaterial synthesis. So later I'm going to explain. Today we are going to do something called the bottom-up approach. So tomorrow we are going to do something called the top-down approach. That's more like a microfabrication and things like that. So today's talk is about bottom-up synthesis of nanomaterials.
Окей. Один из подходов называется bottom-up, снизу вверх. Это, видимо, когда мы строим сложную структуру из маленьких кусочков. Так или нет?
Не знаю, посмотрим.
Сейчас разберемся.
So I'll quickly go through why we want nanomaterials. So there are important length scales going from 10 to the power minus 10 meters buckyballs to soccer ball. So if you look at this range here, so you can see this is the C60, so that's in angstrom level, so then you get to several meters for the soccer ball. If I look at this scale here, so that you can separate into other nanomaterials going from DNA molecules to carbon nanotubes and some other nanoparticles. So this typical length scale for nanomaterials. And that's so you can understand.
Шкала расстояний C60 это фуллерены, да ведь?
So then DNA and carbon nanotube, they have similar scales like nanometers. So then you have other nano particles, several tens of nanometers. So then that's the scale. Then also I want to emphasize there are important length scales. So in physics especially, so we have quantum wells, so you are talking about your length scale about close to 10 nanometers. So then if you go to a single electron transistor, you have the charging energy given by this Kirchhoff over E height. So this length scale is about 10 nanometers. Even in magnetic materials, we have something called the spin flip barrier. So that's given by here. So they all come in nanometer scale. So these are very important. That's why we want to study nanomaterials in this scale. Right?
Это получается, когда квантовые свойства начинают.
Да. Вот эта яма слева изображена, которую мы сейчас обсуждаем, и там энергетические расстояния между энергетическими уровнями характерны, видите, постоянная планка, масса частиц и ширина ямы. И расстояния вот такие вот 27 нанометров. Когда уже вы говорите о заряженных частицах, которые тоже какие-то квантовые свойства проявляются, то шкала по энергиям уже другая. И расстояния возрастают, и спин, чтобы вам перевернуть спин. Да, энергии здесь. Чтобы вам перевернуть спин, справа не вижу, да, там флип сделать спин, а вот шкала по энергиям, там другая, вам почему-то не дает. What was the scale in energy in electron volts?
Electron volts, these are all electron volts, yeah. So then we convert into this L, corresponding L values, they come to in these values here, they are in nanometer scale.
То есть тут обратно, они знают энергию в электрон-вольтах на самом деле, и что по этим формулкам соответствие электрон-вольтам они пересчитывают расстояние. Поэтому считают, что расстояние вот такие же никто измерить не может.
То есть линейку там не приложишь,
а по энергиям они знают, что, поэтому они говорят, должны быть такие, там характерны такие расстояния для электрических зарядов, когда конденсаторов базовые квантовые и магнитных свойств, связанных с переворотным спином.
Yes, yeah, exactly, yeah. Spin out, spin out, yes. So this is just to understand.
I mean, it looks like you speak Russian.
What's that?
It looks like you speak
Yeah,
Russian,
exactly.
you understand almost everything.
Then also there are some scattering lengths. So if you go from elastic scattering So in elastic scattering, so in elastic scattering you can have electron phonon, also electrons getting trapped in impurities. They all have something called scattering lengths. They are also coming in nanometer scale, but much higher length scales. I don't think it is very important. So I just want to, then also there are some screening lengths. So if you take metals, we have something called, I think maybe they are familiar with the Thomas Fermi screening. So typically you have this 1 over R dependence. If you have the screening, it goes like this Thomas Fermi function here. So they all have this nanometer scales.
Закон клона нарушается на очень маленьких расстояниях, и за счет вот этого атмосферных появляется дополнительная энергия. Опять, они, зная энергию, они пересчитывают на расстояние, вычитается, что вот это вот.
Yeah, because metals,
Законом клона происходит на 0,1 нанометра.
so metals you have Thomas Fermi screening. For semiconductors you have electron hole exciton screening length. They call the Debye wavelength. Then for electrolytes, they have something called when you have electrolyte. Okay. If you have electrolyte, if you have electrode, then you have these ions, this electron. We have some kind of electric field across this one. This scale also given by this scale here. So I will discuss this one Friday's talk when you talk about the batteries. I don't think this is very important. So what I want to get here is how to make nanomaterials, right? So this is what I was trying to explain. So when you want to make nanoparticles, you have to start with some building blocks, then you have to assemble it together. So this one we call, put in like this and make the nanoparticle, we call this is bottom up, start from bottom, then you go up. Then, so this includes this chemical, mostly the chemical synthesis. So then also you can start with large block and machine it down to your nanopart size. So that is, we call the top down. So that includes lithography, etching. So this I'm going to talk tomorrow. So today's talk is mostly about this chemical synthesis of this bottom-up technique.
Да. Как я уже говорил, вот bottom-up — это когда мы из маленьких кусочков, из этих билдинг-блоков собираем наноматериал. Это методы powder, это порошок или аэрозоль, или химический синтез. Другой метод — это когда мы что-то большое делим на маленькие части до тех пор, пока это не станет обладать наносвойствами. Вот мы сегодня говорим про левую сторону, в основном, видимо, про синтез.
So first, before we start the nanomaterial, we'll talk about, there are two things you need to have when you grow materials, right? First, you need to have nucleation. So that means you have to have a seed particle. So then you need to have growth. There are two things. First, you need to have nucleation. Yes. You have to have the nuclei, something. Then you need to grow it to large particle. So this is the nucleation. So this is the growth. For any nanomaterial synthesis, you need to have nuclei. So then followed by the growth. Nucleation and growth. I will quickly go through the basic principle of nucleation and growth. So nucleation is if you have two reactants, so then you need to heat it to some temperature, and as a function of time, you can get your final product. So when you get the final product, sometimes you get some byproducts also, right? So then you have to purify and get your product. So this is what I was trying to explain. this is the nuclei, so these are the seed particles. Then they agglomerate they make small clusters. These particles make small clusters, then they combine and make something called crystallites. These are crystallite. Not the crystal, crystallite. So these crystallites then try to agglomerate. So that is the growth. So this is now happening the growth. So then eventually you get the composite particle here. So this is more like a few atoms here, right? And you eventually end up with your large particle. So that's the basic principle for any growth.
Crystallites, it's little crystals.
Crystallite is little bigger than clusters, maybe several clusters.
Это не кристалл.
Это кристаллит.
Кристаллит, это не кристалл.
Not the crystal. Yeah. This, if you have several particles together, you get the crystal.
But the crystallites have some order in the
Yes,
structure.
yes. Crystallite also has a crystalline. Yes.
Ну, то есть, получается, из маленьких частичек мы можем получить кластеры, которые потом соединяются в кристаллиты, и дальше это начинает расти и уже может вырасти в particles, ну, наночастицы, да, в случае nanoparticles. Это самый общий вид, сейчас мы будем рассматривать, как это поподробнее происходит.
Кстати, вот то, что вот занимались наночастицами, это вот как раз вот этот подход, когда мы брали тетрагидрат ацетата никеля или лимонную кислоту, да, как раз два реактанта, стабилизировали температуру, подбирали, получали продукт, по сути.
So this is true for any growth we are going to talk about. So also when you have the first nucleation step, so the first this microscopic clusters or atoms, they form, then the nuclei process begin to structure the crystal, and then you need to have some kind of diffusion. So diffusion, because they have to move. To have the diffusion, we have to have some thermodynamic force. So that can be anything. So you can have some kind of gradient. You can have temperature gradient, or you can have pressure gradient, or you can have concentration gradient. Any of these thermodynamic force should drive it to make the nanoparticle. That's what I explained here.
This force help.
Yeah. So this is the gradient force here. So that's the only way to make the real crystal.
Help to make an order.
Yes. Not only order, it has to move, right?
Окей, да. Получается, когда у нас есть частички, они вот так вот не упорядочены совсем, и чтобы они начали образовывать какие-то кластеры, надо заставить их двигаться, тогда они начнут взаимодействовать, и силы взаимодействия приведут их к какому-то порядку, взаимному расположению. Обычно для этого создаются градиенты, например, градиент температуры, давления или концентрации этих частиц.
So you need to have nucleation, growth, and also you need to have this thermodynamic force here. This one. So this is a very basic idea. I'm sorry. I can use this one. Sorry. Yeah. So if you look at the nucleation, so when the nucleation happens, there are two things you have to think about. There is something called the surface energy, then you have to have a volume energy. So here, typically, if you look at the surface energy, so that is positive value given by, because it's the surface, right? So only this surface is causing that energy. So that will have, if you look at the energy versus if your distance here. So this is typically positive value. So this has 4 pi r squared times your surface tension, right? So this sigma here, yes. So this is positive value, but if you look, this is the surface term, then you have a volume, so that our volume energy. So these are two competing energies. Surface energy, always surface is trying to minimize the surface, then volume is trying to increase it. So the volume energy is given by, it's actually negative term. So negative, that's given by, that's as a volume by R cube times you have this Gibbs energy difference here. It's a function of time. So this is the volume energy, this is the surface energy. So when you add these two, this one plus this one, you get something. Oops.
That's right. That's right.
That's the one? Yeah. Oh, something.
No.
That's okay, I can manage.
Да,
Yeah.
конечно.
Yeah. Oh, yeah. It's vodka.
Yeah. You can vodka between courses.
So when you add these two, you get
Yes.
something. This is going, then this is going down, you get this kind of curve.
Он после водки не рисует.
After what?
Серьезно?
Oh, because yeah, no.
A lot of what?
Yeah.
Я понял.
Huh?
Just right.
What's that? Not vodka?
Снялся от vodka.
So anyway,
Кто
so
принес?
Okay.
yeah, we can see from here. Yeah. So you can see the surface term. So this is the volume term given by this Gibbs energy.
Гамини,
Yeah.
this is the energy per particle. What's the energy? It's the energy of
Energy.
the ensemble.
Yeah, because that's why we have to get the energy difference. So after the crystal is formed,
It's the energy of the whole
whole
system.
system, yes. Yeah, whole system energy becomes like this.
Okay.
So that means it has equilibrium distance. So that R star is given if you
It
take
explains.
the dW or dr. So when you make it 0, you can get that number to be this one. Your delta G is always negative number.
So it explains the ordering.
Or yes, yeah, exactly. And also that energy at that point is given by this value. That is actually called the barrier. So you need to exceed that barrier to grow the crystal. So that's why you need to sometimes heat it or pressurize it or do some thing to overcome that barrier. Because always for the growth you have this, you can see that barrier given by this number here. So that depends on your surface area and also the Gibbs free energy difference. So in order to grow the crystal, you need to first overcome that barrier here.
Все понятно.
Такое теоретическое введение к тому, как образуется кристаллическое, как образуется упорядочение. Вот теория это очень простая. Есть поверхностная энергия, когда увеличивается объем этого кластера. Есть объемная энергия. Поверхностная энергия связана с поверхностным движением, вот кривая и положительная. Есть объемная энергия, которая связана с гибсовским феноменом, вам как бы не очень нужно. Она отрицательная. Когда вы просто складываете две эти кривые, получается вот та вот, которая там синенькая и черная, да. И условие устойчивости это что производная равна нулю по радиусу, и вам нужно преодолеть некоторые барьеры, которые получаются из условия, что производная равна нулю. То есть он объяснил, что упорядочение проистекает только когда мы можем частицы на самом деле сблизить, там, нагреванием, давлением и так далее, но не слишком сильно, потому что нам нужно только преодолеть барьер, чтобы получилось упорядочение. Примерно так, да, или нет, или по-другому это можно прокомментировать.
Мне кажется, что размеры частиц определяются как раз вот этим соотношением энергии. И получается, есть какой-то оптимальный, при котором энергия всей системы минимальна. А дальше, если она хочет расти, то энергия системы увеличивается, это не дает ей расти дальше.
So even in the ordinary case, if we have like two states, right? So if you have some state here, if you want to go here, sometimes you have to go through a barrier here, right? So this is typically, that's where the catalysis, I don't know if the catalysis, if you use a catalyst, you can make this barrier come down, so then you can do like this, then now your barrier is much smaller. So everything is driven by that, the barrier. So if the barrier is low, your nucleation rate is very high. If the barrier is high, the nucleation rate is slow. So that's why nucleation rate is always depends on the energy barrier. So that barrier depends on your surface area, surface tension, and your Gibbs energy difference and temperature.
It's an actual surface tension or any
Yeah,
something
so
like this.
the surface tension for that given material. Yeah. Suppose if you use a gold nanoparticle, the surface tension for that.
Was this one number?
No, yes,
One
yeah,
number.
yes, yeah. So now when you, like I said, we are going to talk about bottom-up approach. When you use this bottom-up, so there are two things we have to think about. One is something called the thermodynamic equilibrium. So that's what we were talking about now, right? You need to have the pressure gradient, temperature gradient. So that means you need to have some nucleation, so growth. So then there's another one called that doesn't need the thermodynamic equilibrium. There's something called the kinetic approach. So in this one, so it limits the precursor you use. So that means if you add the reactant 1 and reactant 2, so that precursor has some limitations on the growth. So I'm not going to talk too much about this one, so don't worry about this one. Let's talk about only this approach. So we are going to talk about this same thing, nucleation, growth, and also we need to have something called the supersaturation. So this is important aspect because suppose if you have some particle, so in some kind of liquid, so if it dissolves in the liquid, so then we have all liquid, right? So then if you add more, still it can dissolve, eventually it gets saturated.
Yeah.
So then if you add more, then it cannot dissolve, then it has to precipitate, right? So that's what here supersaturation means. So forget about this one, so we'll only talk about this approach.
Ребят, ну это про школьные опыты, когда у вас есть какой-то раствор, и вы добавляете концентрацию, он становится перенасыщенным, и потом в нем начинает что-то выпадать. Вот это такой путь.
So then this nucleation, there are two nucleations. We can talk about homogeneous and heterogeneous. Homogeneous means on the same phase. If you have a solid, it's all solid. If it is liquid, it's liquid then liquid. So then we have, other one is the heterogeneous nucleation, that you can have solid in liquid. So that is heterogeneous nucleation. So this is what homogeneous means, either all liquid, all vapor, or all solid. This can be even wave also. Is that okay? Yeah.
No.
Yeah. So we'll So it's only one phase we are talking about, either liquid phase or solid phase or gas phase.
We are talking about this.
This one, yes, yeah, oh, yes. So this one we'll talk later. So you can see, like I said before, you need to have this Gibbs free energy, then you need to have this driving force, in this case, concentration, right? So that will bring me to the final product with the lower delta T.
You mean, do you want a high rate or you don't care? You're talking about
So
this.
sometimes higher rate is good to make more material, but it doesn't mean they are high quality. Sometimes you need to have something in between. Low rate means your product is less, but the quality can be.
And you want to regulate.
Yes, exactly, yes. Yeah. You need to have not too slow and not slow. Yeah.
Вот такие простые вещи понятно, что сказал, если нужно переводить, да, я сказал, скорость, они заинтересованы в высокой скорости образования этих частиц. Но сказал, что вовсе не обязательно, что высокая скорость, качество частиц теряется. Низкая скорость самого материала, но они хотят регулировать этот процесс, чтобы он не случайно шел.
Yeah, we talked about this one. So these are all the things I talk about. Then there's another thing I want to emphasize. There's something called the Oswald brightening. So this means if you start with some small particles, so over the time these small particles try to get together and become large particle. So that means they say it's a fat man becomes fatter if you have, suppose, like this. So if this one come together and make large particle, that will like to take the other particle and make it larger. So that's always happens if you have particles dispersed like this. This is an important thing.
The big particle is
Becoming bigger.
catching.
Yes, yeah. So you can see here, so these are small, nice particles here. Over the time you can see the number of particles are getting less and some particles becoming bigger. Right? So these are taking another one, so then after some times, this one taking more and no particles here, right? Eventually it's taking more and becoming more. So this is happening when you do the nanoparticle synthesis. You have to be very careful.
It's a stochastic process, yeah?
Yeah, it is very stochastic, yes.
We don't actually know which particle will be...
No, we have no idea, we cannot tell that, yes. Yeah. So this is more like, so we have a fat guy, that fat guy becomes fatter. So, small guy disappears.
Понятно, да? Большие ловят маленьких, съедают их и становятся еще больше. Это называется асфальтовое созревание.
Okay, so first let me talk about nanoparticles. So in my talk, first I will talk about nanoparticles. So in this one we talk about metal nanoparticles, then we talk about semiconductor nanoparticles, then we talk about the oxide nanoparticles. So these are all nanoparticles. Then I will go and talk about nanowires and nanotubes. So this is how the talk is. So now I am going to talk about just nanoparticles. So we'll talk about all three nanoparticles. Metal is more like how you make gold nanoparticles, silver nanoparticles, platinum kind of. And semiconductors can be like cadmium sulfide, cadmium telluride. So this any semiconductor nanowire. So oxide can be zinc oxide or tin oxide or any kind of oxide nanoparticles. So each one of them have different properties, right? So first metallic nanoparticles. So if you want to make metallic nanoparticles, what you have to do is you take the metal complex and reduce it in very dilute solution. That's very simple to do. So if you want to make nano gold particles, what you do is take this chloruric acid and boil it in sodium citrate. So this auric means that has gold, right? So this the acid with the gold. This has gold in the acid. So you simply take and use some sodium citrate and you boil it. So then if you heat like 100 C, your color changes in the solution. So once you finish the experiment, you find very stable 20 nanometer, about 10 to 20 nanometer gold nanoparticles in the solution. It's very simple technique to do. So you can do this one if you take the silver acid, like silver acid. If you boil in sodium citrate, you get. So citrate is more like it's a stabilizing agent in this one.
Получается, что один из простых способов получения наночастиц, именно в наноразмерах, это смешать два. Да, то, что вы делали. Смешать два раствора, это как раз те самые прекурсоры, о которых шла речь. Нагреть их, подождать какое-то время, пока цвет не изменится, и мы получим в этом растворе вот такие вот 20-нанометровые с очень хорошей точностью и стабильностью частички.
Yes.
20.
If I use these concentrations, yeah, you can change molarity and your percentage of sodium citrate, you can change this number.
And it is dependent of surface and volume energy.
Oh yes, yeah. That all coming from the, yes.
So Ghamini, it was possible to do 100 years signal, right?
Oh yeah, people did that, remember those days?
But people were not able to observe these particles.
Yes, yeah. But they show the color difference. Yeah, remember there's some ancient, pictures, they have gold,
Like
some ancient church. Yeah, they have different color because we know the band gap changes with the particle size. So that means your luminescence changes, right? You can make different colors for different sizes. Gold nanoparticles, if you go from like 2 nanometers to say 50 nanometers, it changes from red to violet, right? So people have done this one for a long time because it's so simple technique, right? So we just take the precursor and just heat it here.
Some words for students. Ребят, получается, что эксперименты настолько простые, что наночастички могли еще в древности делать, и это действительно так. Если вы про нано залезете в Википедию, там будет фотография чаши Ликурга. У нее очень хитрый такой красивый розовый цвет, и она при определенном освещении начинает еще светиться. Так вот, когда ее начали исследовать, оказалось, что там действительно в структуре наночастицы золота определенного размера, это дает такое свечение. То есть 2000 лет назад нанотехнологии уже были, но у них еще не было микроскопов, чтобы понять, что же они на самом деле делают.
По цвету.
Они цвет ориентируют.
So this you can do the exactly same thing with silver and platinum, palladium, all these particles you can easily do. So now if you want to make semiconductor nanoparticles, so in this one we have to still use high temperature, but we need to heat it in inert atmosphere. So, but we have to use some kind of stabilizing material. For example, if I use some phosphine oxide, and if we use good dispersion, so you can make semiconductor nanoparticles of cadmium sulfide.
Это изолация, это с этим?
Cadmium sulfide, cadmium
Это просто
telluride, cadmium selenide, these kind of nanoparticles we can easily make the same way, but you have to do some kind of organometallic precursor. For example, if I want to use, everybody familiar with the organometallic precursors? So that means you have the metal with some organic compound, right? So you can have, for example, dimethyl, say, telluride.
Dimethyl.
So that means you have tellurium, you have two methyl groups, right? So then you have some tellurium attached to this one. So this is organic with the metal. So this is a metal organic compound. So you have to have that metal organic precursor. So then you dissolve that one in some solvent and heat it in inert atmosphere. So sometimes you have to use some kind of stabilizer. Always you have to have stabilizer to make it not to agglomerate. So if you want cadmium, you can use dimethyl cadmium. And you just dissolve this one in solvent. It can be any solvent. So here we are using phosphine or phosphine oxide. So then just heat it, you make semiconductor nanoparticles.
This is a first precursor.
Yes, yeah.
And we need to add
So then you need to have some solvent. So you need to dissolve it, right? So organometallic. That's the nice thing about, like, if you take cadmium, they don't dissolve, right? That's a metal. But when you have a metal organic compound, that dissolves very easily. That's the advantage of having metal organic compound. So they dissolve very easily in any solvent. With cadmium is a metal, you cannot dissolve it. But organometallic compound can easily dissolve in liquid. So that's this solvent here. So we like to have an anhydride, so like not to have a lot of water.
Получается, ребята, вы меня сейчас поправите. Если нам нужны полупроводниковые наночастицы, мы берем металлоорганическое какое-то соединение, типа вот диметилтелурид или диметилкадмий, да? И растворяем его. Да? В чем? В каком-то растворителе.
What's that?
Which kind of solvents do we need to use?
Something that you can dissolve. That's it. So
What kind of H?
yeah, most of the time people use some kind of organic solvent.
Органический
Yeah,
растворитель.
so like even
Ацетон, бензин.
yeah, even things like acetone or maybe formamides.
And what about the particle? The particle need to have cadmium, for example, and
Yeah, so then you can make the cadmium is not a semiconductor. Okay? You need to have here. So then you have to have cadmium and another one with the sulfur. So then you can make the cadmium sulfide particle. Or you can have cadmium and telluride. So basically, this is most common one. You can use. So maybe telluride. So then you can have, even this one you can have, right? C2H5 with cadmium. So when you dissolve this one in, say, DMF or something, so then you can make cadmium telluride.
Окей.
And
Вот,
then-
получается, мы все это смешали, растворили, и они у нас тогда могут соединиться, и вот это уже будет полупроводник.
So this is the organometallic compound. With solvent you can whatever. Yeah, that's basic idea. So then oxide nanoparticles. So this is the most easiest thing to do. So you can easily there are several methods to do that one. So first, homogeneously you can just dissolve the whole oxide particle and just do like we did for the metals. But mostly people do something called the salt gel method, so I'm going to talk about that one. So if you familiar with, this is one of the most silicon dioxide, right? Or aluminum. So these are very I think popular oxides. So this we can easily do by salt gel technique. So I'll talk about the salt gel technique now.
Maybe we can have 5-minute break?
No, that's fine, yeah. Oh, problem.
Progress.
Yeah. So after this one, let's have a break. So after salt gel,
Okay.
let me quickly go through the salt gel one. So salt gel is simply very simple process. You start with something called the metal alkoxide. So this means this, if I want so everybody familiar, I don't know, the alkoxide, alkoxide is, this can be methyl, ethyl or anything. So if you have methyl alcohol, methyl oxide, so that means you have CH3, or you have H, then you have O. This has a negative charge. So this is called the methyl oxide. So you can have ethyl oxide or any alkoxide. So that alkoxide, if you hydrolyze, that means if you dissolve it in water, they make this small colloid. We call it colloid. So colloid is, so this colloid is, we call the salt. It's like this is a salt gel technique, right? This is called the salt. So once you make the salt, then you can do anything. If you want to make a film, first you make a film. You just put it in the salt and deposit on as a film, or you can spin it and make kind of a fiber, and you can do anything like that. So after that you have to do second process called the gelation. First you make the salt, then you have to do the gelation. So when you do the gelation, that means these salt particles, they agglomerate together and make the big particle here. So this is salt, then it becomes gel here. So then if you remove your particle or heat it and remove the solvent, you get this particle. So that's the salt gel technique.
Понятно из картинки? Растворчик делаем, коллоидный получается. И потом
Chemistry people are very familiar with salt gel technique.
Потом его можно нанести хоть куда, хоть на основу, хоть вот на ленту, а потом высушить, и получается тот самый гель из этого золя. Слова не русские, а так вроде все понятно. Ага.
So if you want to, this is how that, if you take this, this is your, this alkoxide, so when you hydrolyze, so you make this salt, so after gelation you make this gel, so then you can heat it or maybe evaporate it, so then you make the gel. So gel is becoming longer chains, so after drying, so this still has the solution inside, right? If you remove, you get the simple, the aerogel sample. So
It's very white.
like, yeah. So you can make very simple forms like this one. Yeah. So if you want, you can look at the reaction. This is what happened. So this is the silicon, this structure. Here you can see OR is this O, R means this thing. So RO means methyl oxygen. So then this is for silicon. We are going to make silicon oxide, right? If I want to make this one, you start with this one. This is the hydrolysis. So this first step is this hydrolysis. What happens is, you can see this one OR group is replaced by OH group here, right? So then next step, when you do the gelation, so this HO, they combine and make a longer chain. So then in next step, again these two combine and then it becomes bigger and bigger. It's like polymerization.
Looks like polymerization.
So if somebody wants here, is the real reactions with water, so then how they polymerize here.
I want to try to do this with my students.
Yeah, this is very easy technique to do. Salt gel is, for any oxide, this is the easiest way to do. Salt and gel. So after this one, maybe let's take, so you can see, if I use for the silicon nanoparticles, you can see how nice, how monodispersed, right? They are very equal diameters. So we start with silicon alkoxide, then sometimes you have to use a catalyst to make it faster. So you can, solvent can be anything, you can use any alcohol, then just put water to make the gel, then after gelation, you get this nice particles. Very straightforward. You want to take a short break? Or?
Yep.
Yeah.
Ребят, давайте немножко проветрим, то я чувствую, что мы выдышали.
So how many of you have chemistry background? All of them?
A little background.
Yeah.
But there is only one professional chemist.
Oh, she's chemistry. This is mostly chemistry here. Yeah. Yeah.
Тут на паузу можно?
Да.
А где тут пауза? Там старт.
Нажми на красный.
Там старт.
И следующую запись начнем. Кирилл склеит.
It's a critical temperature. So that is, you supersaturate the precursors. So then it will start making materials. It can make nanoparticles, and also you can make even nano wires also.
Wires.
So if you look at, so this is how that autoclave is. So this is typically stainless steel container. You can open it, fill with, sometimes we call it a bomb because it's a high pressure, right? So you heat it to high temperature. Sometimes this typically we call it autoclave. Yeah, autoclave. So sometimes people call it a bomb. So basically, you put the reactants, dissolve in whatever the solvent, then put it inside, close the vessel, then heat it to above the boiling point. You have to boil it. So then you can use typical oven or even microwave oven. So this is how zeolites are made in large quantities. Zeolite is some oxide, so that is like a cage structure. They have this some middle pore structure, so then you have other structures. So the middle you have a large open pore. they have very large surface area. So this is some kind of silicate. So this aluminum silicate, I think. So we have aluminum, silicon, and oxygen, something. So this is a very good catalyst. Look at.
Эта штука называется цеолит по-русски, и это катализатор.
This is a perovskite material, yes. Yeah. So we have some aluminum, silicon, and oxide. This is very commercial material. People make zeolite using the hydrothermal. It's very easy. You just take aluminum precursor, silicon precursor, and dissolve it in the solvent, put it in the autoclave, close it, put it in the oven, and heat it.
Can we use this like a filter?
Oh yeah, that's what people mostly use. Yes, this is something called a separator. It's like a filter for even separate different gases. So if you have carbon dioxide, nitrogen, oxygen, so you can filter some gases, other gases will be trapped here. Yeah, this is called the separator or filter. So this is always used for that purpose. Yeah. And also catalysis. This has a surface area is about, you can get about 1,000 meters square per gram.
Oh.
Yeah, that's very large because it's all pores, right? It's all not much material here. Zeolite is very important substance. Yeah. So you can easily make using the hydrothermal. So you can see, so this hydrothermal synthesis of even other like cadmium sulfide, cadmium selenide, that also you can make, like I said, cadmium, you can make sulfur, selenium, or any of these. You can use using this technique. If you start with cadmium, this oxide, if you use this kind of solvent, then put it in the autoclave, heat, then you get these nanorods or nanoparticles. Remember, Uliana, she made graphene quantum dots using the hydrothermal. I think you were also part of that. No, I think Sergei Mushinsky, I think. So they made quantum, graphene quantum dots using this technique.
Ребят, понятно, да, получается, что растворили, нагрели это в автоклаве под большим давлением, и получается вот такие вот нанороды.
These are all very easy techniques, very simple. You need to have that autoclave, that's all. You just mix, close, put it in the oven, heat it, that's all. You get the material out. Very simple.
Печек на кафедре много, автоклав можно соорудить.
So next one, I'll talk about nanowires and nanotubes. So far we talked about the nanoparticles, right? So if you want to make nanowires and nanotubes, so we know why nanotubes are important. So if you make nanowires in single crystal formation, so they have very good crystality in one direction. So your transport can be very fast in that direction, but not in other directions, right? So
do we have a dislocation in the center?
yes, yeah. Sometimes you have some dislocation and even point defects kind of thing. But if you make good growth, you have very good crystalline material. Very, yeah. So it's easy to control defects on nanotube and nanowires rather than on films.
Да, получается, про нульмерные штуки мы поговорили, про частицы, теперь одномерные усы кристаллические и нанотрубки, как они получаются.
So when you want to make nanowires and nanotube, there are three techniques we use. Something called the spontaneous growth. So that has, this is the most important thing. We call the VLS growth. This is vapor, liquid, solid growth. This is the most famous one, VLS. So this means vapor. This is liquid. Then you have the solid is your nanowire, right? So, or you can have this something called the SLS. That is also not very common. This is solid, liquid, and solid, yes.
And all of these phases are...
No, start with this one. So then, I will explain how that one works. Yeah. So next one is template growth. Template growth, that you can find this something that has nice templates, like if you have something that has nice good pores like this, right? So then you can put your material here. So then now if you remove your template, you have the wire here. So that's called the template growth. So last thing is the electrospinning. You can spin your, this you need to have some polymer. So what you do is you have some metal, needle. So if we put something here, so then you can pressurize this one, right? Suppose something like this. It's like injection. You just press this one, so this is coming out, right? So then we apply large voltage, electric voltage between, this is your, suppose some plate here. So this is metal needle, so your injection needle. So, yeah, so then if we apply some large voltage, this is a metal plate. So it's like you keep the metal plate like this, you have your the triggers and the syringe like this. So now this is a metal, right?
Yes.
So if we apply something like kilovolts, very large voltage, so we are pushing this one. So you can put this one to something called the syringe pump. This is slowly pushing this one, so that means they are slowly coming out. When it comes out, you have a large electric field here, right?
And then it moves.
Yeah, it just spin like that. So then on the screen, you can find a lot of nanofibers. So if you look at this one, you see nice fibers everywhere.
And fiber will be, for example,
it comes and just breaks it, so then it falls onto this one.
Or they will be grown from...
No, so it's mostly coming from here.
Ага, вот эти.
Yeah.
Стреляет.
Как макароны получается.
Да, стреляет просто.
Okay, and we will move?
No, we just move this way. So this will spread very long. If you look from here, you will see like a spider web, like that. These fibers everywhere. It's very easy to do. You only need this injection syringe. And this one also you can slowly push by hand also, but we use the pump. So that will.
And it's what size of?
Fibers you can make something like maybe hundreds of nanometers. So then, good thing is you need to have some kind of polymer here. So then at the end you can remove the polymer. Then you can have your nanowire.
Okay.
These are the three techniques to make nanowires and nanotubes. Let me quickly go through. This one is not important. So I'll start from this one. VLS growth. I think this is very important. So in the VLS growth, you need to have something called catalyst here. Suppose if I want to grow silicon nanowires. No. If I want to make silicon nanowires, you have to start with the some catalyst. So catalyst can be any metal. So this is why this is kind of interesting. If I use gold particle as a catalyst, so that is your actual liquid. So this is the gold particle. Then we have silicon, because we are going to go silicon nanowires, right? We have silicon vapor that you can have like silicon in gas phase, like we know silicene, that's a gas, right? Or you can have some other silicon vapor. You can even take a silicon particle and use a high power laser. So then you can vaporize it, right? Then you get the silicon vapor. So now you have this silicon vapor coming here. Now this is gold, that's a solid, but you have to heat the sample. When you heat, gold becomes a liquid, right? So you have gold liquid, now the gold becomes a liquid. Now silicon you have in vapor. So then the silicon will dissolve in the liquid, right? So then it becomes, we call the silicon gold alloy. So then more silicon come in, so then it dissolves, so then it becomes saturated. So after saturated, it grows as a solid. So that's why you have liquid gold, you have silicon vapor, then silicon will precipitate as a solid. So that's the VLS growth.
Ребята, смотрите, как интересно, да? Капелька золота, на нее садится пар кремния, и потихонечку в капельке его становится так много, что он начинает расти на подложке. А капелька остается сверху, и рост продолжается до тех пор, пока в атмосфере есть пар, и пока капелька может его оттуда брать. И это катализатор, значит, он не портится, да, и все растет, пока мы этот процесс не остановим. Прикольно, из пара в твердое состояние.
So you can use gold, or sometimes you can use iron also. But there are many catalysts you can use, iron, gold, any of these catalysts. You can grow silicon, germanium, even binary alloys like gallium arsenide, gallium phosphide. All these nanowires you can easily grow using this technique. So this is VLS growth. But when you do this one, you need to understand a little bit something called, I don't know if you're familiar with these phase diagrams. So this typically we draw temperature versus this is the material percentage. This means zero gold, and this means gold concentration. No, here you have all gold. This has all silicon. So in between you have this different alloy concentration.
Yeah,
right?
all of them know that.
Okay, you familiar with two technique. So you can work, because we know here is everything is solid, right? So here you have liquid. So this is where you have to do the growth at some temperature around here, because we need to have liquid phase, and so you need to understand a little bit what temperature to operate this one. So this is the eutectic percentage here.
Точка эвтектическая.
So if you do that using gold nano particle, you can get very nice silicon nanowires. sometimes at the tip you will see the gold particle, because there are two ways they can grow. There's something called the bottom growth. So in that case, so you have your gold particle here, silicon is coming like this. Sometimes this gold can move with silicon. Yeah. Sometimes you find gold here. Yeah. Depending on which way. So that's a VLS growth. So you can see even other materials you can make using this one, like gallium arsenide, all these things you can. In this case, you need to have, if you want to make gallium arsenide, you need to have gallium vapor and arsenic vapor, right? With the gold particles. So easiest thing to do is the laser ablation.
Yeah.
Then if you use the gallium arsenide vapor, I can make a plume of gallium arsenide by laser pulse, so then you have gold particle, it will go. This is eutectic diagram for gold and gallium arsenide. So these are the people who have done all these nanowires using this VLS growth, gallium arsenide, all these things. You can easily make. Look at the nanometers are only like 2-3 nanometers. Minimum, yeah. So it varies. So very highly crystalline material. Your direction. So here there are some other nanowires grown by VLS technique. Here is the one I was talking to you about. So you have the catalyst particle, then the vapor comes here, then it starts to grow like this. Over the time, it becomes fatter and fatter. Right? Short to grow. You can see in this case you have particle at the top here. So you can do the same thing for carbon nanotubes also. You can do exactly the same way. So in that case, you have to have gold, or actually for the carbon nanotubes, gold doesn't work. So for that you need to have iron, because iron and carbon, they can mix easily. So gold and carbon, they don't, so we call the miscibility, right? So, but gold and silicon, they are good, so they call the miscibility is there. But gold and carbon, they don't mix. So for carbon, best thing is iron particles. So if you use the iron particles, you can do the same way. Like you, here is the, you take some carbon, the graphite, you put the laser and ablate it, then you get carbon vapor. So then you have iron nanoparticles. From there you grow carbon nanotubes.
It's only one nanotube?
No. It's a lot of nanotubes. Yeah. But you can grow one nanotube like this. If I have a substrate, if I can put gold nano or iron nanoparticles like this, that you can do. I have done this one. So now if I use carbon, then I can make one nanotube from one of them. That we have done. I have science paper based on this one.
Where is growing nanotubes? On iron,
So
nanoparticles and grow?
No, yes. What happens is, again, iron, when we have heat to high temperature, at high temperature iron becomes liquid. So now carbon comes and they dissolve in iron. So after supersaturation it will precipitate like that. So this carbon you can get from laser ablation, or I usually use methane gas. I have high temperature methane gas decompose into carbon and hydrogen. Okay? This carbon will dissolve here and go from. That's very easy to do.
Ребят, тут понятно получается, что нагреваем лазером лазерная абляция, лазерное испарение материала, то есть короткие, очень мощные импульсы, сразу испарение без плавления происходит. У нас получается атмосфера, насыщенная углеродом. И этот углерод начинает расти на точечках железа, которое мы туда поместили. И таким образом можно получить высококачественные углеродные нанотрубки. Гамини, no, not vertical.
No. So, but you can grow vertically. There's something called the super growth. They are called the nanotube forest. So that's very still people don't understand. The technique is to introduce little bit water. So what happens is, so when you grow this one, the iron and carbon, they are coming together, right? Eventually they will make this iron carbide. So this is a bad catalyst. So, but if you have water, so they will prohibit this carbide formation. So that will make it grow longer and become vertical. You can make something called the nanotube forest. It looks like a lot of nanotubes as a forest here. That's called the super growth.
Вы видели этот лес?
So for this you need water. So there's some work doing that way. So initially people grew carbon nanotubes using this arc discharge. So this is, you have two graphite rods, like two rods like this. In one you mix with iron. So you take graphite, when you make a pellet, you add iron particles. So then you bring them closer and apply very large voltages like that. Then it's arc. When it arcs, it consumes one electrode. So then you can, on the outside wall, everywhere you can collect nanotubes. This one. So this you can make large quantities from this reactor.
То есть раньше надо было взять два стержня, один из них еще намешать углерод с железом, подать большущее напряжение, дуга возникает, и вокруг нее начинает расти на другом стержне вот эти самые нанотрубки. Мне кажется, что верхний способ гораздо симпатичнее.
So this way you cannot make large quantity. This way you can make kilograms. Yeah. So my previous boss, he started this company. So he made a lot of money. So
for mass production.
Oh yeah. So he made a lot of materials and he became very rich. So we were helping him to make these electrodes. Our job was to just mix with iron particles and make this electrode. He started with small electrodes. At the end, he made like almost this big, long electrodes. So he made a lot of money from that.
And for the next step, you have a lot of nanotubes on electrode.
Yeah.
And you need to clean it.
No, it's all deposit on this reactor. This is a cylindrical big reactor. It collects all over the wall. So, but when you open the chamber, you have to be careful. It will all fly away, right? So then what we do is we spray some ethanol or something so that it will not fly away. Then you can take it like a big mesh. It's like a cloth. It's coming a lot of material. It's nice, this arc discharge.
I'm thinking about the boxing.
No, it's more like a cylinder. So large, I'm talking about this long and this huge one. So this is the way to make carbon nanotubes. Now if you go to graphene, so in graphene what we need is, we should not have that carbon dissolved into the particle, right? So for that you can use, iron is good because carbon is not going to mix with gold. So then it will just spread So that's why people started with copper. So if you have copper substrate, when you introduce this methane gas, so the carbon, they don't really mix here, so they just deposit on the surface. So then you can find graphene on the surface. So if you use copper, yes, yeah.
Copper это медь.
So if you use simple copper foil, like if this is my copper foil, so when you after growth you find graphene covering the entire copper foil, because nothing is going into the copper, because carbon and copper miscibility is very low. If you use like iron, because they dissolve and eventually grow like tubes.
Okay.
But in this case, because of zero solubility, this is the important thing. Zero solubility, so then carbon atoms directly grow on the surface. You can see if something goes in, that will again come out and collects on the surface. There's some carbon now, that one.
And we didn't have extremely fast cooling. Yes.
Yeah, typically after the growth, usually we just open the furnace. Yeah.
And it will be enough.
Yeah, that's enough.
Structure.
Yeah. Yes, we need to make sure all the atoms are coming into the surface. Yeah. Sometimes there are some atoms getting diffused into the copper foil. So when you do fast cooling, it will all come to the surface.
Смотрите, ребята, иногда получается хороший эксперимент, это когда ты просто открыл печку. Не подбирал какие-то условия специально, не охлаждал в жидком азоте или геле, а просто открыл и оптимальные условия.
So then last thing, I'll just quickly show the template assisted growth. Like I said, so you have this alumina substrate, they have tiny holes like that. So if you want, you can even make that tiny holes using this technique actually. When Sergei Mushinsky, when he was at Louisville, he made these things using simple electrochemical etching. So anyway, important thing is if you have this template, you just fill those pores with your material. If you want gold, you just fill with gold. You can do from vapor or by liquid. You can, I did a lot of work with this bismuth telluride. Bismuth and tellurium, you can melt very easily. So when you melt, you can fill those pores with the material. So at the end, you just put this one in sodium hydroxide. So the template will dissolve. Then you have this wires just freely floating in sodium hydroxide. You can see a lot of particles coming, going like vertical. So I will stop here.
Ребят, по последнему слайду, мы создаем темплейт, образец какой-то. Его можно просто лазером, а потом туда помещаем материал, удаляем лишнее, получается периодическая структура, но в ней каждая точка выросла вашими усилиями, а не случайным образом и не упорядочилась за счет энергии.
So that's very simple, right? If we have any pillar, like some open tubes, you just fill with your material, then just remove the support. Then you get the, but they are not highly crystalline. Okay, so I will stop here. It's too much.
Thank you, Gamini.
Thank you.